So this is about quantum error correction, the topic of quantum error correction. You can see some basic information on the first slide. The information already mostly communicated. This is actually my own group logo here. I invented it myself. So we begin with the topic of quantum error correction. I hardly need to tell anybody present in this room that one of the biggest enemy of quantum computing is decoherence. As far as I'm aware, that this was Bill-Unruh who first pointed this out in this clarity back in 1995. And because Peter Shaw has had a rather vested interest in the fact that possibly quantum computing can work, he just said, okay, I mean, there's a possibility that one can have some very highly efficient quantum error correction schemes, shortly thereafter in PIA. But usually the active correction of error syndromes is necessary. So one has to apply recovery operations to bring back the system into the code space in a suitable manner, or one in the broad context of quantum control one can operate, or one can put this under the broad context of quantum control. Such a control, quantum control, is experimentally realized in various systems, in ion traps notably, and in superconducting circuits. I mean, I just always give a couple of references because there are far too many to quote everything. The alternative to active quantum error correction, so active schemes to correct errors which are incurred on the code space, is autonomous quantum error correction, the topic of this talk. The autonomous quantum error correction is basically a variant of the quantum Zeno effect, so that you continuously watch a system in the right way. I will explain what is the right way. That you continuously watch a system to lead it back to the code space, which will be corrupted, this code space, but still it will be the code space, as I will show. So the dissipative quantum error correction, I think basic idea was found by Wojciech Zurek here in this paper, continuous error correction. And the general context which I will be talking about is the so-called dissipative quantum state engineering. This goes back in its original idea, I think, to the paper of Almut Beige et al. With Daniel Brown and Peter Knight here back in 2000. And then the Peter Zoller group has worked this out in many, many publications in a different context, in a different variety, but it's the broad context of dissipative quantum state engineering. And with respect to quantum computation, I think Verstraete, Wolf, Serac have been about the first to mention this possibility. The autonomous quantum error correction scheme has been proposed and realized in certain specific setups. It's proposed in nanophotonic circuits here, in circuit QED, and also realized in circuit QED, and proposed in ion traps very recently by the group of Peter Zoller, or around Peter Zoller. What I will propose here we are there. The screen appears again. So why did it turn off? So the main topic of this talk, I hope that the fact that the screen vanishes, or did vanish, did not mean something specific. At that very moment when I want to mention the main topic. So I propose an implementation independent, general sufficient criterion for autonomous quantum error correction, and show in particular its long-time scaling behavior, how well it works with respect to the error incurred. And in particular, I will make no a priori assumption on the structure of the error correcting codes in distinction to these works. So our context, general context, also the general context of dissipative quantum state engineering, will be that of a Lindbladian evolution. And what I assume in that Lindbladian evolution is that I have two parts. I will put, first of all, the Hamiltonian here to 0 by suitably engineering the engineered Hamiltonian of some external system, which I couple to the system of interest. Then I will assume I have intrinsic dissipation, so unavoidable dissipation. I cannot control it in any way, which is something I have no real control about. But then I also assume at the same time I have the possibility to engineer dissipation in a suitable manner. This is given by this part here, and I will assume that the engineered dissipation is very, very large. I will assume that this M here is much larger than 1. We will see later on that in the specific implementation I will propose, circuit QED, M already has been realized to be of order 100, and even 1000 is in principle possible. The typical intrinsic single bosonic mode Lindblad operators are the single particle loss, single photon loss, and decoherence, which is proportional to the phase, the conjugate operator to the phase operator. So, the title of the talk contains the Knill-Lanaprawamme condition, so I explain now what is the Knill-Lanaprawamme condition. For those of you who does not know what is the Knill-Lanaprawamme condition? About half of the audience. Okay, so I need to explain it. If you consider a certain code space, which means something on which you can do error correction. So this is this span here. I consider d-dimensional code, so that's why there's qudits in the title. If you consider a certain code space with the indices mu and mu primed, and you have certain errors, generally there will be Krauss operators, but I consider the short time limit here. So the error operators can be these aforementioned two and the unity. The Knill-Lanaprawamme condition reads as follows. You have a matrix which depends on the index of the code of the errors, and this matrix should be, that's the crucial part, should be independent of the errors, and it's just multiplied by the unity matrix. The Knill-Lanaprawamme condition means physically, because this thing here, the C matrix, is independent of the code space indices mu and mu primed, that the system, the error correcting, the environment which causes the errors, intrinsic dissipation, does not gain information, in inverted commas, does not gain information about the code space, or the code states in the code space. And in effect, the Knill-Lanaprawamme condition is the very basis of any quantum error correcting scheme, because it defines the computational useful logical qubit space on which error correction can be performed at all. So this is peculiar here. It didn't happen in any talk before, right? I pressed it twice. But why does it happen specifically? No, I do nothing.
They put escape.
Okay, so this defines the logical qubit code space that the Knill-Lanaprawamme condition is satisfied. The remainder of the talk. And now we need to construct the engineered jumps. They have engineered operators. We first of all define subspaces of dimension m by the union of the code words, W for word, in the code space, with something which is generated by intrinsic errors, Fk, acting on the code words. Then we construct an orthonormalized basis. I use another index here, I, from this, which of course a priori is not orthonormalized. We construct an orthonormalized basis for this space here. And then we define the engineered jumps to be of two varieties. One of them is corrective. This means this corrective part here, this part, pumps back the error-corrupted states to the code space. Code space, error-corrupted. So this pumps back this part here. That's corrected. This goes up to n-1. And the rest here is composed to be of preventive operators. These guys here are from the corrupted code space. So from this space essentially here. And these guys here are from the space where we do not want to go to, namely the space, the rest of the Hamiltonian space, H minus SCCS, outside the code space. So this prevents that states leak out into a part we do not like. That's why it's called preventive. So this we're supposed to be these the engineered jumps. I should stress that this part here is essential, but this part can look different. Can be. No, this is really a nuisance here. Okay. The decomposition now I will do of the intrinsic dissipative evolution is the following. I will have to walk you through now like 3 slides, which are a bit more formal even. So I hope you, until I show you the main result, but I hope you can keep the attention. So I decompose now the intrinsic evolution, this is the intrinsic part of the dissipative evolution, into one part, which is using the projector to the code space in this way. So a part projected to the code space. I can always do that. And the rest, which is obviously the rest. I call these two guys Fk and Fk tilde. So the projected part Fk, Fk tilde, the rest, this part here. The result which I will get, or which I will describe now, is a noiseless subsystem symmetry. The noiseless subsystem NSS, I will use this as acronym, concept was invented by Knill-Lanaprawamme and Viola, already 8 years ago. And I will argue that when this part here, the second part is 0, and if this second part is not 0, but if m goes to infinity, then I have exactly a noiseless subsystem symmetry in the system. The properties, I cannot explain them in detail because of the lack of time, but I just mentioned them here. The properties responsible for the noiseless subsystem symmetry is that as mu, these guys here, these guys, these corrupted code space guys, are collecting subspaces. That is, the initial states which are there never ever leave these subspaces. And as a corollary, that these spaces support unique steady states. The details of this are in this paper. It essentially has to do with the fact that the projectors to these spaces as mu, they commute with all possible in-blood operators. That's the essence of these two properties here. And the last property I need is that there exists a stationary phase coherence between two different S mu and S nu. The stationary phase coherence between the two different spaces here is established by a so-called unitary intertwiner, which can be constructed in this way from the code space vectors and from the corrupted code space vectors. These guys here are just, again, vectors outside the corrupted code space. And the crucial property now for the existence of the stationary phase coherence between S mu and S nu is that this unitary intertwiner commutes with all F, which are among these here. So this Fk part of the intrinsic dissipation is projected to the code subspace, and all engineered operators, all strongly dissipative Lindbladians. And then all stationary states, this is the consequence, are unitarily connected in this fashion by this intertwiner, and all states evolve unitarily in the corrupted code space. So although the code space is corrupted, all states unitarily evolve in this corrupted space. So this is the noiseless subsystem symmetry I was referring to. It's the coherence and dissipation-free evolution, although FK corrupt. The details are in this preprint here, the technical details. I can show, possibly one can remember a picture always a little bit better. I can show a graphical representation of the noiseless subsystem symmetry. What you see here, this is the code space where you have these squares. These guys here is the code space vectors, code space density matrix. This part here is what is the corrupted code space minus the code space. Yeah. And this F tilde here, this remaining part of the intrinsic dissipation evolution, is what breaks the noiseless subsystem symmetry. So this is the remaining part which causes still dissipation, actual dissipation. The main result, which we then get by an expansion in powers of 1/m, is that the error caused by Fk tilde vanishes. So this, that effectively in this limit m goes to infinity, the noiseless subsystem symmetry is exact. And that we can derive, and this is also distinguishes from every other previous work, we can derive an error bound for the integration at the integration time big T, which reads as follows, the error being defined as this. This is the Lindbladian evolution. And the error exactly scales like this. 1/m, so vanishes obviously, and m goes to infinity. Gamma is here the total intrinsic dissipative strength, so the measure of the total intrinsic dissipation, and T is in the aggregation time. So the error bound is solely determined by this ratio here. Gamma, the intrinsic dissipative strength, and m. So now, in a physical implementation in the remaining like 3 or 4 minutes, is in circuit QED. Circuit QED, as I think known to most people here, this is basically that you have a 2-level system in a Cooper box coupled to a superconducting resonator, which is then the same like cavity QED. Of course, vastly different energy scales, or to some extent vastly different energy scales, but essentially the same, exactly the same Hamiltonian. So for the theoretical physicist, the same. And then in such a circuit QED system, you can emulate the intrinsic dissipation I need here by L. L is the number of intrinsic dissipative operators, fast decaying qubit ancillas, rapidly decaying with the rate kappa I. This has been done in, proposed such a model to engineer the required dissipation by Zanardi et al. In a paper back in not too long ago. So the coupling Hamiltonian is of this variety. Lambda is a coupling strength. This is the engineered Lindbladian. This is the excited state of the qubit ancilla, the ground state. It decays rapidly. And in the recoupling limit, the scaling of the engineered dissipation required is of this form. You see it's a simple second order result. It's of this form, and you can plug in the numbers from the experiment. Most recent one at Yale is this one. And there they achieved m equals 100. So m very, very large is not a bad idea. And as I say, they can go in principle to quite some factor bigger. And how does the code perform, or how does one code perform within our setup? Just to show you a picture here so that you can possibly remember a picture, always easier than formulas. We used it, our scheme, for the binomial code, which was recently proposed in this PRX paper here. The binomial code is a specific error-correcting code with binomial coefficients. I think I don't need to explain this in detail because you just believe me. So the simplest code words are these two. This is we have a Fock space with maximally 4 photons. So we have 1 photon, 2, 3, 4. These are the simplest 2 code words for a qubit, these 2 guys. Then one can show that the engineered jumps, which we need. The engineered jumps, which we need. these guys here, they read for such a system like this. This phi here are simply arbitrary states in the corrupted code space. And then we can average the fidelity defined in this manner over, for example, we can average over 6 initial states of this form, just to give an idea. And the average fidelity is then depending on M. So you see it increases. This is just the physical qubit without any error correction here. This gray line, this gray solid line, and already M equals 10 outperforms it significantly. M equals 100 is already pretty good, and M equals 1000 is very, very good. So to come to the conclusion, what I try to convince you is autonomous quantum error correction is feasible in a general setup independent manner by strong engineered dissipation. It provides full protection against decoherence when the quantum Zeno effect of the engineered dissipation is arbitrarily big. But this might sound a little bit trivial, but we derived the actual scaling of the error with time, which is, as far as I know, not contained in any previous work in a general implementation independent manner. I showed you an implementation in circuit QED where large M is possible. Finally, to mention the context of quantum metrology, the first version of our preprint we had it contained, but then the referee forced us to kick it out, but still I want to mention it. If you want to estimate a parameter in a system Hamiltonian which is multiplicative in this manner here, with some generator G, then one can show, because of the unitary evolution, that the temporal Heisenberg bound is reachable for the estimating this parameter. And finally, for the details, this is contained in this paper, which was posted in its version 2, which contains this fidelity plot 1 week ago. And this is took together with my undergraduate student, Lim, and a former undergraduate student of mine, which is now at the Yale Quantum Institute. Thank you for your attention.